Black holes, those cosmic enigmas, are regions in spacetime where gravity is so intense that nothing, not even light, can escape. For centuries, their existence was a theoretical curiosity, a mathematical quirk arising from Albert Einstein's general theory of relativity. But with the advent of powerful telescopes and sophisticated observational techniques, black holes have transitioned from scientific speculation to established astronomical objects, challenging our understanding of the universe. The very concept of a black hole seems to defy the fundamental laws of physics we observe in our everyday lives. From the conservation of information to the nature of time itself, black holes appear to be cosmic rebels, bending and, in some cases, seemingly breaking the rules that govern the cosmos. This video explores the profound ways black holes challenge our understanding and push the boundaries of scientific inquiry. Let's begin with one of the most perplexing challenges, the information paradox. In quantum mechanics, a fundamental principle states that information cannot be truly destroyed. Every particle, every interaction leaves an imprint, and this information is preserved, even if scrambled or hidden. But what happens to this information when it falls into a black hole? Stephen Hawking famously proposed that as black holes evaporate over eons through a process called Hawking radiation, the information about what fell in would be irrevocably lost. This idea sent shockwaves through the physics community, as it directly contradicted the foundational principles of quantum mechanics. Imagine throwing a book into a raging fire. The book is destroyed, but the information contained within its pages, its atomic structure, is still theoretically recoverable, albeit incredibly difficult. Now imagine throwing that same book into a black hole. According to Hawking's initial theory, the black hole would eventually evaporate, leaving behind only thermal radiation, devoid of any memory of the book's contents. This would mean that information, a cornerstone of our universe, could be permanently erased, a truly revolutionary and unsettling thought for physicists. The black hole information paradox ignited decades of intense debate and research. Many physicists found it difficult to accept that a fundamental law of nature could be violated. They proposed various solutions, each with profound implications for our understanding of gravity and quantum mechanics. One proposed solution suggests that the information isn't destroyed, but is instead encoded on the event horizon, the point of no return around a black hole. This idea, known as black hole complementarity, posits that from the perspective of an observer far away, information seems to bounce off the event horizon. However, from the perspective of an object falling into the black hole, nothing unusual happens at the event horizon. It simply crosses an imaginary boundary. This dual perspective creates a profound tension, as both views cannot simultaneously be entirely true without violating other physical principles. Another intriguing concept is the firewall paradox. If information is indeed preserved at the event horizon, it might imply that a firewall of high-energy particles exists there, instantly incinerating anything that crosses it. This would contradict Einstein's principle of equivalence, which states that freefall is indistinguishable from zero gravity. If a firewall truly exists, an astronaut falling into a black hole would experience a fiery demise at the event horizon, rather than smoothly crossing it as predicted by general relativity. This is a direct contradiction that challenges the very fabric of spacetime as we understand it. The information paradox and the firewall highlight the deep incompatibilities between general relativity, which describes gravity on large scales, and quantum mechanics, which governs the subatomic world. Black holes, in essence, are where these two pillars of modern physics clash most dramatically. Beyond information, black holes also challenge our understanding of causality, the principle that effects follow causes. The singularity at the heart of a black hole is a point of infinite density, where the known laws of physics break down entirely. Within the singularity, spacetime ceases to exist in the way we understand it. Time and space swap roles, and all paths lead inevitably towards this central point. This means that past, present, and future effectively merge, rendering the concept of causal relationships meaningless. Imagine a universe where every direction in space is essentially down, leading you to the singularity. In such a realm, the arrow of time, which normally dictates progression from past to future, becomes ambiguous, if not entirely absent. The existence of singularities also poses a problem for the cosmic censorship hypothesis, proposed by Roger Penrose. This hypothesis suggests that all singularities in the universe are hidden behind event horizons, preventing them from being observed directly. If naked singularities, singularities not cloaked by an event horizon, were to exist, they would fundamentally break predictability in the universe. Information could emerge from them without a discernible cause, leading to a breakdown of determinism. The idea that black holes could host naked singularities challenges our core understanding of how the universe operates. It implies that at times, events could occur without any preceding cause, which would be a radical departure from everything we know about physics. Let's consider the concept of time dilation near a black hole. According to general relativity, gravity warps space-time, and this warping affects the passage of time. The closer you are to a massive object like a black hole, the slower time passes relative to an observer far away. For an observer falling into a black hole, time would appear to pass normally. However, to an outside observer, that same individual would appear to slow down, eventually seeming to freeze at the event horizon, never actually crossing it from their perspective. This relativistic effect creates a strange paradox regarding the fate of information. If an object takes an infinite amount of time to cross the event horizon from an external perspective, how can it ever truly enter the black hole and be subject to the information loss? This question further underscores the deep mysteries surrounding black holes. The discrepancies in observation, depending on the observer's frame of reference, highlight the counterintuitive nature of extreme gravitational environments. Black holes also challenge the law of conservation of energy. While it's generally understood that energy can be neither created nor destroyed, but only transformed, the powerful jets emitted by some supermassive black holes raise intriguing questions. These relativistic jets, observed extending thousands of light years into space, are thought to be powered by the accretion disk of matter swirling around the black hole. But the sheer amount of energy involved is staggering, sometimes exceeding the combined light of billions of stars. Where does this immense energy come from? While some is converted from the gravitational potential energy of infalling matter, it's theorized that the black hole's spin and magnetic fields play a crucial role in extracting and channeling this energy into the jets. This process, while seemingly adhering to energy conservation through transformation, pushes the boundaries of efficient energy conversion. The mechanisms by which black holes generate these jets are still not fully understood, but they represent some of the most energetic phenomena in the universe. The very existence of supermassive black holes at the centers of galaxies also challenges our models of galaxy formation and evolution. These gargantuan objects, millions or even billions of times the mass of our Sun, appear to co-evolve with their host galaxies. The relationship between a supermassive black hole and its galaxy is a profound mystery. Does the black hole drive galaxy growth, or does the galaxy's evolution dictate the black hole's growth? Or is it a symbiotic relationship where both influence each other? One theory suggests that the energy output from active galactic nuclei, powered by supermassive black holes, can regulate star formation in their host galaxies. These powerful outflows could heat and expel gas, preventing it from collapsing to form new stars. This feedback mechanism is a crucial component of modern cosmological simulations. Without it, scientists struggle to accurately model the observed distribution of galaxies and the rate of star formation throughout cosmic history. Black holes also play a role in challenging our understanding of spacetime itself. General relativity describes spacetime as a dynamic fabric, warped by mass and energy. Black holes represent the ultimate warping, a tear in the fabric. The idea that spacetime could be so utterly distorted that a region becomes causally disconnected from the rest of the universe, where even light cannot escape, is a profound and almost poetic challenge to our intuition. Albert Einstein initially doubted the physical existence of black holes. His equations predicted them, but he found the implications too extreme, too much of a departure from his understanding of a predictable and ordered universe. Yet observations have repeatedly confirmed their existence, from stellar mass black holes born from the collapse of massive stars to the supermassive varieties lurking at galactic cores. They are not merely mathematical constructs, but active cosmic entities. The discovery of gravitational waves in 2015, emitted by colliding black holes, provided direct evidence of these space-time distortions. It was a monumental achievement, opening a new window into the universe. Gravitational wave astronomy now allows us to hear the universe in a whole new way, detecting the cataclysmic mergers of black holes and opening up new avenues for understanding their properties and behavior in extreme gravitational environments. These mergers are not just energetic events. They are also a powerful probe of general relativity itself in its strongest possible gravitational regime. Do Einstein's equations hold up in the face of such extreme spacetime curvature? So far they do. Black holes also challenge our fundamental understanding of what constitutes space and time. Inside the event horizon, the future always lies at the singularity, and the past is behind the event horizon. This means there's no going back. This inescapable journey creates a unique temporal landscape, unlike anything else in the universe. If you could somehow survive the immense tidal forces, your future is predetermined, locked onto a path towards the singularity. The interior of a black hole truly represents the ultimate frontier of physics, a region where our current theories break down, and gravity exerts its absolute dominance over all other forces. Could black holes be portals to other universes? While popularized in science fiction, some theoretical models, like the notion of wormholes, propose exotic shortcuts through spacetime. However, stable, traversable wormholes remain purely hypothetical. The intense gravity of a black hole could theoretically connect to another region of spacetime, forming a bridge. But such a bridge would likely be incredibly unstable, collapsing before anything could pass through it. Furthermore, creating and stabilizing a wormhole would require exotic matter with negative energy density, a substance that is currently unknown and may not even be physically possible. So, while the idea is fascinating, black holes currently serve more as space-time cul-de-sacs rather than cosmic highways. They are destinations of no return, where everything ultimately converges. Another aspect where black holes challenge physics is in the very definition of nothing. A black hole's interior is often described as empty space, yet it contains the mass of a collapsed star or even a galaxy. This question delves into the nature of space-time itself. Is it a stage upon which events unfold, or is it an active participant? Black holes suggest the latter, where space and time are fundamentally altered by the presence of mass. The concept of a black hole, an object from which nothing can escape, means that even its gravitational influence propagates outward at the speed of light. But what about the interior? The interior region, beyond the event horizon, is a causally disconnected realm. Events inside cannot influence events outside. This absolute barrier is a powerful demonstration of the speed of light as the ultimate speed limit in the universe. Black holes also challenge our ideas about symmetry. When a star collapses to form a black hole, many of its properties, like its chemical composition or intricate magnetic fields, are seemingly erased. According to the no-hair theorem, a stationary black hole can be completely described by only three external parameters: its mass, its angular momentum spin, and its electric charge. All other details about the collapsed object are lost. This loss of information about the initial conditions of the collapsed star challenges the deterministic nature of physics, where knowing initial conditions should allow us to predict future states. Imagine throwing an encyclopedia, a romance novel, and a comic book into separate, identical black holes. After they form, all three black holes would be indistinguishable, despite the vast differences in their initial states. This phenomenon implies a dramatic simplification, where the intricate complexity of a star is reduced to just a few fundamental parameters. It's like nature simplifying a highly complex equation to its simplest variables. The no-hair theorem is a powerful statement about the nature of gravity and the ultimate simplicity of these extreme objects. It suggests that, in their final form, black holes retain only the most fundamental attributes. Ultimately, black holes serve as cosmic laboratories, pushing the boundaries of our understanding of physics. They compel us to confront the limits of our current theories and to seek a more complete, unified description of the universe. The quest to resolve the black hole information paradox, to understand the nature of singularities, and to unify general relativity with quantum mechanics are some of the grandest challenges facing modern physics. Each new discovery, each new observation of black holes brings us closer to unraveling these mysteries. From the direct imaging of supermassive black holes by the Event Horizon Telescope to gravitational wave detections, we are slowly peeling back the veil. These enigmatic entities are not just cosmic oddities, they are profound probes into the fundamental nature of reality. They are where the rules we've come to expect occasionally seem to bend, if not break entirely. The exploration of black holes forces us to question our preconceived notions, and to embrace the possibility that the universe is far more strange and wondrous than we can currently imagine. As we continue to study these cosmic rebels, we are not just learning about black holes. We are learning about the ultimate fabric of space-time, the nature of information, and the deepest laws that govern our universe. pushing the very limits of human knowledge. The intense gravitational forces around a black hole also lead to extreme tidal forces, colloquially known as spaghettification. Imagine a body being stretched infinitely thin as it falls towards the singularity. This stretching effect, where gravity pulls more strongly on the parts of an object closer to the black hole than on those further away, would literally tear anything apart before it reached the singularity. This dramatic phenomenon highlights the immense differential in gravitational pull. While a human would be torn apart long before reaching the event horizon of a stellar mass black hole, supermassive black holes are wide enough that spaghettification might occur closer to the singularity. The boundary of a black hole, the event horizon, is not a physical surface, but a region of spacetime. Crossing it is not like hitting a wall, but more like crossing a river, where the current eventually becomes faster than you can swim. Once you cross this invisible boundary, the fabric of spacetime itself is flowing inwards faster than the speed of light. No matter how fast you try to move outward, you're inevitably carried towards the singularity. This point of no return is a direct consequence of general relativity and showcases the absolute power of extreme gravity. It fundamentally changes the causal structure of the universe for anything that enters. Black holes also challenge our models of particle production and vacuum energy. Quantum fluctuations in empty space near the event horizon can lead to the creation of particle-antiparticle pairs. This process is crucial to understanding Hawking radiation. If one particle of a pair falls into the black hole, the other can escape, carrying away a tiny bit of the black hole's mass energy, causing the black hole to slowly evaporate. This incredibly slow evaporation process, which would take vast eons for even a small black hole, means that black holes are not eternal. They have a finite lifespan, albeit an exceedingly long one for most observed black holes. This idea that black holes can eventually disappear, converting their mass entirely into radiation, further amplifies the information paradox, bringing us back to the question of what happens to the information they swallowed.